Another object which illustrates mechanical energy well is the pendulum. The pendulum is just a mass hanging from a spring under gravity. And it usually looks something like this. Instead of drawing the floor for once, we're going to draw the ceiling. And there's a string or maybe a cable hanging down, and you've got a mass like that. The mechanical energy here is the kinetic energy of the mass, and we will just do UG because there's no spring here. We just have the gravitational potential energy. And we know as long as this is isolated, as long as nothing goes pushing on it, then that's constant. It's conserved. So what happens with a pendulum is when you get it swinging, you have times when it's up here. And it goes up here, it stops, and it falls back, and then here it's going back and forth, and then it goes over here. And it goes up here and stops, and it falls back, and it goes back and forth. And as it's doing this, you're converting. The total energy is constant, but you're converting between kinetic and the potential of gravity. And we have one here. So here is bowling ball hanging from the ceiling. And here it's at rest, right? So it has zero kinetic energy, and we'll define this as zero potential energy. We'll say this is the zero for potential, since potential depends or is always a change. And now I'm going to do some work on it to get it going. So I'm going to get it swinging, let's say out to here, and there it goes. Now I've left Al there so you can see roughly where zero is. That was in the rest position. So now as we watch it swing, you can see this is the lowest it goes right here, and it's also the fastest it goes. So its energy is all kinetic right here. And then if we follow its trajectory out a little bit, up here is the highest it goes right there, and that's also where it stops. That's where its energy is all potential right there. So in these kinds of problems, you might be asked, you have a pendulum. It goes a certain speed. When it crosses its rest position, how high does it go? Well, from the speed, you can get the kinetic energy, and then using energy methods, you could say, okay, all that kinetic energy I calculated is now due to potential, and that tells you how high it went. Right? So the pendulum is a very nice, simple case that you can use to illustrate this and use it to solve problems. One thing, though, it's interesting about the pendulum, since we have conservation of energy, since the energy is constant, it never goes higher than where you release it from. Right? If you think about it, when you release it, you hold it back, you give it some gravitational potential energy, you give it some UG, it has a certain amount, it's not moving, it has no kinetic, and when you release it, it converts that gravitational potential into kinetic, and it goes up here to the same height if there's no external influences, and then it comes back. And when it comes back and stops, there's no way it could be higher because it has the same amount of energy. As long as you started with zero kinetic and you end with zero kinetic, it has to be the same height due to the law of conservation of energy. So here's a well-known way to prove the conservation of energy. We bring the ball way over here, and I climb up so that I can get in its path. Then I get backed up against the wall, and what I'm going to do is hold it up against my chin and release it. And it's going to swing all the way across the amphitheater. But when it comes back, it's not going to hit me in the face because it can't get any higher because of conservation of energy. It can't gain any energy during the swing. So physicists love to do this demo because of all the drama, but really for a physicist, getting hit in the face, I mean, you know, doesn't really matter. But anyway, it's a good demo. So here we go. I'm going to release. And I'm not worried at all because I know there's really no way it could possibly hit me.